Imagine an object right in front of you. It has mass. It takes up space, but you cannot see it. Your eyes perceive only the scene directly behind it, as if the object itself were a hole in the fabric of reality. This is not a scene from a Hollywood blockbuster. It is not magic or a trick of the eye. This is the tangible, emergent world of invisibility science. Scientists are not making people vanish into thin air. Instead, they are learning to command the very medium of our perception: light. The invisibility we are achieving is more subtle, more complex, and in many ways far more profound than fiction ever imagined. It is a fundamental manipulation of physics. The core concept is surprisingly elegant. It is not about making an object transparent. It is about making light itself forget the object was ever there. Think of a large boulder in the middle of a smoothly flowing river. The water parts to move around the stone, then seamlessly rejoins on the other side. An observer downstream would see an uninterrupted flow, unaware of the obstacle that briefly parted the current. Scientists asked a bold question: could we do the same with light? So, how do you build a cloak of invisibility? The answer lies in a revolutionary class of substances known as metamaterials. These are not materials you dig out of the ground or find in nature. They are artificially structured composites, engineered with repeating patterns smaller than the wavelengths they influence. Their properties come from internal geometry, not chemistry. They are the physical embodiment of a mathematical idea, interacting with light in ways no conventional material could. It is alchemy for the 21st century. Every material has a property called a refractive index. That number shows how much light slows and how much it bends. Water has one refractive index. Glass has another. Metamaterials can have a refractive index that varies point to point. They can be engineered to have a negative refractive index. Negative refraction makes light bend the wrong way, something once thought impossible. By arranging tiny structures, scientists create a gradient that steers light around a central volume. Imagine a vast array of microscopic antennas. Imagine tiny metallic split rings. Each element is smaller than a wavelength of light. When a light wave passes through, it interacts with these elements and they re-radiate the wave. By controlling shape, size, spacing, engineers control the phase and direction of the re-radiated waves. Achieving invisibility in the visible spectrum is a Herculean task. The wavelengths of visible light are measured in mere nanometers, hundreds of times thinner than a human hair. Fabricating metamaterial structures at this scale with the required precision is at the very edge of our technological capability. Furthermore, most cloaking designs work only for a very narrow band of frequencies. A cloak designed for red light might fail completely for blue light, causing the cloaked object to appear as a bizarre, colorful distortion. This is known as chromatic aberration. It means a true, broadband invisibility cloak that works for all colors remains a distant dream. But our senses and our technologies perceive more than just visible light. Every object with a temperature above absolute zero radiates energy in the form of infrared light, which we feel as heat. Military night vision and thermal cameras are designed to detect this signature. A person hidden by a visible light cloak would still appear as a glowing human-shaped silhouette on a thermal imager. Therefore, a true cloak must also be a thermal cloak. Scientists are now designing thermal metamaterials that can guide the flow of heat. Instead of bending light, these materials channel thermal energy around the cloaked object, making it appear to have the same temperature as its surroundings. The quest for invisibility even extends into the strange and wonderful domain of quantum mechanics. Some theoretical physicists are exploring the idea of quantum cloaking, which could hide events, not just objects. The concept involves manipulating the quantum field in a region of space-time to create a time gap. An event could occur within this gap, but any probe passing through would detect nothing, as if the event never happened. The implications of this technology are as vast as they are unsettling. It is no surprise that military and defense agencies are among the most interested parties in invisibility research. The strategic advantage of true stealth is almost absolute. Imagine a fighter jet invisible to radar. Imagine that same jet invisible to thermal detection. Imagine it invisible to visual detection. Imagine a surveillance drone hovering in plain sight, completely unseen. Imagine ground troops moving across a battlefield without casting a shadow or showing a heat signature. This could rewrite the rules of modern warfare. The pursuit of military dominance drives scientific innovation. But placed elsewhere, that power becomes profound societal risk. Consider the erosion of privacy. If a small, effective cloaking device becomes available, how can any space be secure? Unseen cameras placed anywhere. Individuals moving through public spaces undetected. Individuals moving through private spaces undetected. Criminals bypassing security systems. Espionage or terror executed with unprecedented stealth. This threatens trust and accountability. A threat could be anywhere, at any time. We stand at a fascinating and precarious moment in history. The wild, imaginative dreams of science fiction are slowly crystallizing into the hard reality of the laboratory. Invisibility is no longer a fantasy. It is an engineering problem. We have established the physical principles. We have built the first crude prototypes. We have demonstrated that, within specific limits, we can command light and heat to conceal an object from detection. The path forward is one of refinement, scaling the technology, overcoming the immense challenges of manufacturing and broadband application. But the direction of travel is clear. The impossible is becoming possible. The progress is steady and relentless. Each year, the cloaks become more efficient, the range of cloaked frequencies widens, the fabrication techniques improve. The science is not just about making things disappear. It is teaching us to control light and energy with a precision we have never had before. This will lead to revolutionary new technologies, hyper-efficient solar panels, medical imaging with unprecedented clarity, and computers that operate at the speed of light. This is the principle of transformation optics. The goal is to create a cloak that bends the path of electromagnetic radiation, visible light, microwaves, radio waves. The light that enters the cloak from one side is channeled around the central region, and then exits the other side on its original trajectory. To an outside observer, the light rays appear to have traveled in a straight line, as if nothing was there to block them. The object nestled within the cloak is rendered invisible because no light has interacted with it. It casts no shadow. It reflects no light. It is a ghost in the machine of the universe. This journey from theoretical physics to laboratory reality has been slow and deliberate. It is an endeavor built on the shoulders of giants, from James Clerk Maxwell, who first unified electricity and magnetism, to the modern pioneers of nanotechnology. The challenge is immense. It requires us to build materials with properties not found in nature. We must engineer matter at a scale smaller than the wavelength of light itself, creating intricate architectures that can perform this incredible feat of optical illusion. The invisibility we have today is limited, imperfect, and confined to specific conditions. But it is real. These expanding frontiers of cloaking technology highlight a crucial point. Invisibility is not a single monolithic technology. It is a collection of different techniques for different parts of the electromagnetic spectrum. One layer to absorb or redirect radar, another layer to cloak its thermal signature, and perhaps a crude, active camouflage system for visible light. Each layer would be a specialized defense against a specific mode of detection. The result would not be perfect invisibility, but a layered adaptive deception. A shimmering glitch in an enemy's sensor array, creating a ghost that is there one moment and gone the next. We must grapple with these ethical questions now. Development follows a familiar pattern, like nuclear energy, like artificial intelligence, initially complex, initially expensive, initially controlled by large institutions. But technologies tend to become smaller, cheaper, more accessible. What if you could 3D print a cloaking device at home? The power to render things invisible is the power to control what is seen and what is known, to control the narrative of reality itself. That power should inspire deep caution. Scientific promise is alluring, but don't be blinded by its brilliance to the shadows it casts. The pursuit of invisibility, like the space race before it, will spin off countless innovations that will change our world. It is a testament to human curiosity and our unyielding desire to master the forces of nature. But as we celebrate these triumphs of ingenuity, we must keep our eyes wide open to the consequences. Every powerful technology is a double-edged sword, and this one is sharper than most. It holds the potential for a future of perfect stealth and absolute deception, a world where our own senses can no longer be trusted. The ability to hide an object is one thing. The ability to hide a person, an action, or a truth is another entirely. We are building a tool that could, in the wrong hands, dismantle the very notion of an observable, shared reality. The challenges it poses are not just technical, they are deeply human.